some not so much, but if you
Mm-hmm.
have some that you can verbalize, let's go ahead and get started. And then if you see a problem that you want to go over that you can't verbalize, go ahead and take a picture and send it, and we'll work on that when I get it.
All right. So kind of what we're doing right now is like relative maximum, relative minimum points of inflection.
Okay?
And so far I think I've been pretty good with that, but
You have some problems that we can do?
I do. These first ones, I think what you're supposed to do is it says find all points of relative maximum and minimum and points of inflection. And yeah, I think that's it.
Okay.
So this first one here is f of x equals x cubed minus 3x squared.
So what's our first step?
Let's take the derivative of that, right?
That's pretty much the answer every time you ask that question.
Mm-hmm.
When you're doing calculus, the first step is almost always take the derivative.
Mm-hmm.
What do you get?
So that would be 3x squared minus 6x.
Now, where are we going to find our relative mins and maxes?
Be where the derivative is equals 0.
Okay. Now, solve that. How do you solve that?
You can factor 3x out of it, looks like.
Leaving
X minus 2.
Okay. Now what?
And so then you'd be able to solve it for where x would equal 0 and x equals 2.
So now how are we going to tell which one's a maximum and which one's a minimum? You're correct. That's one of them's likely to be a relative minimum and the other is likely to be a relative maximum. We do, after all, have a cubic, and cubics tend to look like this.
Mm-hmm.
Okay. So how do we figure out which is which? It's a simple way. There's actually two ways. But to me, the one way is really the better way to use if you can use it. You can't always use it. Sometimes you can. And the second part of that question asks about inflection points.
Right.
So what do I know I'm going to have to do at some point?
Use,
Take the
or
second.
I guess, right, yeah.
What's the second derivative?
The 6x minus 6.
Okay. Now, the one thing we're looking for is, we're also interested in concavity, right?
Right.
So if I take these 2 points that I came up with, 0, 2, and I plug them into the second derivative, is all I want to know is whether it's positive or negative. If it's positive, it means it's concave up. Associate up with positive. If
Right.
it is negative, it's concave down. So what is f double prime of 0 equal to?
-6.
Just negative. It is -6, but I only care that it's negative.
Right. So it'd be
0,
concave down.
yeah, let me just put a grid on this thing. Right there, it is concave down. So that makes it what? A maximum or a minimum?
Maximum.
Yeah, anytime it's concave down, it's a max. Now, we can't be certain that the 2 is up until we run the test. What is f double prime of 2?
Just be positive 6.
Yeah, that matches the fact that it's a minimum. And that's where 2 is there. Okay.
Okay.
So we've got our concavity, we got our relative mins and maxes. The last thing is the inflection point. How do we get the inflection point?
That one I actually don't know because I missed.
Set the second derivative equal to 0.
Yeah, I missed Monday and Tuesday of this week, which is when we were doing that.
Okay. Solve that for x, and you'll have your inflection point.
So it'd just be x equals 1.
Yeah, which is right there. And the inflection point is the point where the concavity changes. In other words, we go from a concave down to a concave up situation. You can't get from one to the other without there being a middle point somewhere. And that's what the inflection point means.
Okay.
It means a change in concavity, and it's always where the second derivative is equal to 0. So
Okay.
this problem, we needed first derivative and second derivative to do all of it. Now, occasionally this second derivative test will not tell you whether it's a maximum or a minimum because it won't always come up positive or negative. Sometimes it comes up 0. Okay? In other words, let's look at this one right here. If that were to have come up, let's not do that one. I don't want to confuse you with having 2 zeros. Let's say this one came out to be 0. Then
Okay.
not use the second derivative test to tell whether it's a minimum or a maximum. I have to go back and use the first derivative test. And the first derivative test, to figure out minimums, you want the slopes to be going negative, 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 and come out positive, positive, positive. That's the first derivative test. If the slopes are positive, 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 coming out negative, 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 then that's a max. If the slopes go from negative to positive, that's a min. So you don't need the second derivative test to figure out whether it's a min or a max. It's just a lot easier because the other way, the first derivative test, is you have to make up numbers to the left of 0, plug it in to the first derivative formula, and see if it's plus or minus. So I would have to plug in maybe minus 1. Well, if I plug in minus 1 here, I get a positive number. That means my slopes to the left of that critical point are plus. And then if I plug in plus a half, somewhere right there, I'll get a negative number, meaning my slopes come out of the peak negative. Well, if it goes in positive, comes out negative, it must be a maximum. So, second derivative test is by far the easier one, but it doesn't always work. When it comes out 0, it's not working. So you have to go back and rely on the first derivative test.
Okay.
Okay.
I think that makes sense.
Yeah, it's a little complicated. But if we do a few of these, I'm sure you'll, I don't even know. They may not give us one where the second derivative is 0. So, you know what I mean?
Mm-hmm.
That would be a particularly difficult problem. Whereas the one we just did was easy because I didn't run into any chinks. I didn't run into any kinks in the armor, problem like the second derivative being 0.
Mm-hmm.
All right.
Yeah, it was the first one on the page, so they probably made it the easiest.
Yes, for sure.
All right, maybe this one will be a little harder. Looks like f of x equals x squared plus 1, and that's over x squared minus 9.
Okay. Same things they want?
Yes.
Okay. This is hyperbolic in nature, right?
Mm-hmm.
Meaning it's going to look something like this. If it looked like that, there would be no maximums, there would be no minimums.
Mm-hmm.
And trying to find them, we'll find that out. In fact, it's going to be hard even if I put in asymptotes. Where are my asymptotes? My vertical asymptote's going to be.
That is something I'm very rusty on.
Well, it's wherever the denominator is 0. So set x squared minus 9 equal to 0. And that gives you your 2 vertical asymptotes.
So 3, negative 3.
Uh-huh. So that's the beginning of our graphing this thing. Now, I know they didn't ask you to graph it, but we're going to be able to tell quite a bit by graphing it. How about a horizontal asymptote?
Forgot how you do that one.
It is the ratio of the coefficients of the x squared term.
Oh, that's right.
Only that when the degree is the same in the numerator and the denominator. In other words, these x
come back to
cubed over x cubed, and the horizontal asymptote would still be y equal 1. But if it was x squared over x cubed, then the horizontal asymptote is at y equals 0.
Mm-hmm.
In other words, if the bottom is a higher degree than the numerator, the asymptote's always at 0.
Right.
Okay, so there's my grid. Now, these curves tend to look like this. First of all, got that part of the hyperbola. And then I got to do something in between the two lines. And frequently, it can do that. And then it comes out on the other side of the vertical asymptote, like that. So if our graph ends up looking like that, you see any relative mins or maxes?
No.
The only other way it's going to look, these have one of two shapes. And the other way is where it goes up, doesn't reach the horizontal asymptote, comes back, turns around like that, and then the other side would look, it would be up here.
Mm-hmm.
And so the other possibility is the curve's going to look like that with, in other words, that, and this. And that does have a relative maximum right here.
Mm-hmm.
So there might be one or there might not be one, looking at it graphically. So we've got to do the math and figure it out. Okay? Now, my eraser doesn't work on this program, so let me start from the bottom. X squared plus 1 over x squared minus 9. X squared plus 1 over x squared minus 9 is f of x. Let's start taking derivatives. It's another thing. If you don't know where to begin, take the first derivative. Mm-hmm. Although, I think it was helpful to point out that graph because it's important to know that you may not find any critical points.
Mm-hmm.
First thing we have to do is to find the first derivative. So how do we get the first derivative here?
Looks like you'd have to do the quotient rule.
Okay. So fill in everything for me.
So we'd start with the bottom.
Okay.
For
And
D.
parentheses are important here.
Mm-hmm. So then it'd be times the derivative of the top, which would just be 2x.
Okay.
Then minus just the top, x squared plus 1, times 2x again. And that's all over the bottom squared.
Okay. Now, for that to be equal to 0, what has to be true?
The top has to be 0.
Yes. In other words, I could just know that if you have a quotient that's equal to 0, the numerator has to be 0. It's the only way you can get it equal to 0. The other way to look at it is I can multiply both sides by the bottom, and this goes away. So basically, I can ignore that and look at the top. So let's see if we can simplify that and solve it and see if there are any places where we have a flat tangent line. What do we got here? We got 2x cubed minus 18x minus 2x cubed minus 2x. 2x cubes cancel, and I get minus 20x equals 0. X is 0. Okay, well, that would lead me to believe that it's the blue picture, right?
Right.
Whereas if we're looking, let me put the whole thing in blue. Whoops, didn't do it. Huh? That's weird. That's really weird. Oh well. If this is the picture, well, right there at x equals 0, we do have a flat tangent line. So it's almost certain that this is our model. It doesn't go straight up in between the vertical asymptotes. It turns around and comes back down, giving you a flat tangent line at x equals 0.
Could it also be the opposite of that?
That's the only answer we got. We didn't get multiple places. In other words, we only have one critical point. So I suppose, oh, that's ugly. If I had to tell whether it was concave down or concave up at that critical point, how am I going to do that?
You need the second derivative for that, right?
Yeah, you see how ugly that's going to be?
Yeah.
The last thing in the world you want to have to do in calculus is apply the quotient rule twice in a row.
Yeah.
It presents a nightmare. So let's use the first derivative test instead.
Okay.
And here's why we can do it. Is the only thing we need is whether the first derivative to the left of 0 is plus or minus. That'll tell us what the slopes are. And I think they should be plus if my picture is right, correct?
Mm-hmm.
In other words,
right.
If that blue picture was correct, to the left of 0, you're going to have plus slopes. To the right of 0, you're going to have negative slopes. Well, this bottom is particularly what? always plus. When you take a
Right.
number and square it, it turns positive.
Mm-hmm.
I know the denominator is 0. The numerator ended up being minus 20x. So I'm dividing 20x, this is the first derivative test, and I want to try a number to the left of 0, for example, negative 1. With me?
Yeah. So you just get 20.
Which is plus. 20 divided by a plus is plus. So my slopes to the left of 0 are plus. And here's what I thought I was looking at that matches that.
Right.
I know the slope is 0 right there. Now what is the slopes to the right of 0?
They'd be negative.
Correct. If I plug in a positive 1 for x, I get negative 20 over a plus sign. So by the first derivative test, I know that that is a relative maximum and it's concave down.
Okay.
Now, inflection points. We can, I mean, not that, how much freedom do you have for using your calculator on some of it? Do you get to graph it?
Yeah, we usually get our graphing.
You're allowed to graph it when you take a test, or always, sometimes,
Yeah, always.
always? Well, I don't know what's going on here. I lost. Let me close it out and try opening it up again.
I guess there wouldn't be any inflection points for that one, would there be?
Exactly. In other words, if you get to graph it before doing all the math, then you kind of don't need to do any math.
Mm-hmm.
Right? In other words, if I'm looking at this graph, and let me see if I can draw this sucker properly. You know the graph I'm talking about. It's those two and this one.
Yeah.
Okay. If I graph this thing first, and I see this graph, I'll see that there's no inflection points. There's only one critical point. I can even see that it's at x equals 0. In other words, I know everything I need to know by just graphing it. I don't need to do first derivative, second derivative, first derivative test, none of that. If they didn't allow you to use the calculator, then you would.
Right.
You'd have to do it the mathematical way, which was this way.
You'd say, if possible, always graph it before you start.
Yeah, I suppose. Yeah. Because you could have gotten the graph, the first one I drew, and that didn't even have any local minimums or maximums.
Mm-hmm.
Now, let me just bring up one thing you're probably aware of, but if you're not, let me make you aware of it. If I have this function, y equal x cubed, if I take the first derivative, I find that there's a critical point at x equals 0.
Mm-hmm.
It's not a local maximum or minimum. If I take the second derivative, in other words, I think something's going on at x equals 0, but is it a local minimum or maximum? Well, if I take the second derivative, it ends up being 0. This is one of those cases where you don't know anything by the second derivative. In other words, at x equals 0, the second derivative is 0. So neither the first derivative or the second derivative tells me whether that's a local minimum or maximum just from the algebra or just from the math. So I do have to do the first derivative test. I have to go to the left of zeros, and I will discover these slopes are positive. I have to go to the right of 0, and I will discover those slopes are also positive. If the slopes don't change, you do not have a relative maximum or minimum. You only have a horizontal tangent line. In other words, it's possible to have a horizontal tangent line without it being either a minimum or a maximum. For it to be a minimum or a maximum, the slopes have to be different on either side of the relative extrema.
Mm-hmm. Does that mean it's an inflection point?
It is an inflection point. In other words, if I do take the second derivative and set it equal to 0, that solves for the inflection point. I know it's right there. And I can see that it's there because that's obviously concave down, that's obviously concave up, and that sure looks like the in-between spot.
Okay.
Okay. But the main thing I'm trying to point out is just because the first derivative is equal to 0 does not mean you automatically have a relative extrema.
Mm-hmm. Okay.
You do have to do the second derivative test and make sure that it's not equal to 0. As long as the second derivative does not equal to 0 at that point, then it is going to be a relative extrema.
Okay.
Okay. What happened? Let's see. Did we finish this problem? I think we did. Was there anything other that we didn't answer on this previous problem?
No, I think that was it.
They only asked for maximums, minimums. They did ask for concavity, I guess, didn't they?
No, but I guess they could ask for that on like a quiz or something.
That's concave up from negative infinity to the first vertical asymptote. It's concave up from positive 3 to infinity. And it is concave down from negative 3 to positive 3.
Right.
Now, how did I know this was up here and not down here?
That is a good question. How did you know that?
Well, if you work from right to left on these hyperbolic functions, I'm not going to say 100% of the time because I can actually think of some where it's not true. But any problem you're going to run into, I'm going to tell you 99% probability. If you work from right to left, notice that I head to positive infinity there.
Mm-hmm.
I got to come out from negative infinity on the other side of that asymptote.
Okay.
When I draw this line, I'm going down to negative infinity as I approach the next vertical asymptote, going right to left. That means I got to come out from the other side from positive infinity. So that's how I knew to put it up in that upper left quadrant and not down in the lower left. If it had been down here, then I'd be coming up from negative infinity again. Now, there are some really complicated functions that can do this, that don't follow the rule I just told you. So it's a really general rule of thumb, but I think I've maybe seen one in 8 years that didn't follow this rule.
Okay.
A simple one, I can give you a real simple one. Y equals 1 over x squared doesn't follow that rule. If I graph that, it looks like this. I do have a vertical asymptote at 0, but notice on the right side of that vertical asymptote, I'm going up to infinity, and I'm coming down from positive infinity on the left side also.
Mm-hmm.
So where that rule doesn't tend to work is when you have a net squared in the bottom. Not a squared, a net squared. In other words, the difference between the top and the bottom is x squared. In other words, something like x squared over x to the fourth plus 1. That is liable not to follow my rule because it's got a net x squared in the bottom. So
Right.
that tends to produce stuff like that. In fact, the hardest problem I think I ever saw was they gave us a really complicated graph and they said come up with a function. And it was brutal. It took me like 20 minutes to do it. You kind of got to work backwards. In other words, they give you the function, you figure out where your vertical asymptotes are, figure out whether it crosses the horizontal asymptote. That's another thing. Functions can cross the horizontal asymptote. In other words, one possible picture here was for it to cross the horizontal asymptote. They just can't cross vertical asymptotes. They can also cross oblique asymptotes. All right, I think we've killed that problem to death.
I think so. These I'm probably gonna have to send you a picture of.
Okay.
He likes to give us some where he shows us the graph of the first derivative and then
I would say that there's a lot more calculus problems you're going to need to send pictures of than not. Although those are the harder calculus problems too. In other words, the easy calculus problems are the ones you can verbalize because all you're doing is reading a function and then we're taking the first and second derivatives of it. But anything that includes a graph, that's pretty impossible to verbalize. So, you still have my email? Send my email, not my phone?
Yeah, I can do that.
Okay.
Just give me a second here.
Yeah, just tell me when it says sent. And send it as a large file attachment. Where things are brutal this time of year. Do you go through the 21st of December also?
I think so. Yeah.
Yeah. It's going to be busy for me for the next 3 weeks.
Yeah, I bet.
Oh.
What's your email again?
It's davidcowan1949 @gmail.com.
All right.
Type in just the DA, it should bring up a default for you. Or maybe not. Have you ever sent me anything?
I think I have. It just came up.
Okay, so my default should be in your phone. It's COWAN.
Right.
Okay.
Yeah. Just
I had a misspell it once. They misspelled it COWEN, and then I had to correct it. And then every time they sent me an email, they would get 2 defaults, and they didn't know which one to send me. So the last thing in the world you want to do is misspell it the first time, or know how to get rid of your defaults. I personally don't know how to do that on my phone, but in other words, how to remove a default.
Yeah.
Misspelled one.
Well, it says I've sent it now.
It says it's sent?
Yeah.
I haven't gotten it yet. There it is. Okay.
Looks like it's a little sideways there.
That's okay, as long as I can download it. In other words, as long as you send it as a file attachment, then I can download it, open it with my editing program, and I can rotate it.
All right.
Whereas if it's embedded in the email, I can't do that. And it wouldn't work if it was sideways. But this will work just fine. What are the instructions? Oh.
It's just you have to.
Yep.
There on the right.
These are fun. Yeah. No, this is one of the more difficult things to do in calculus also, where they give you the derivative and they want you to figure out the function.
Mm-hmm.
Now, the one thing we're going to be able to do is figure out the function, but not where to place it vertically. You'll see. So, what do I know the function is doing from -4 to -1? My derivative is positive. From -4 to -1. What does the function have to be doing if the derivative is positive?
Has to have a positive slope.
Has to be increasing. If the original function is increasing, the derivative is positive.
Right.
I've always found it helpful here to show a picture from my archives. Let me do it real quick, just in case you've never seen this. Surprisingly enough, I've seen only one calculus book out of about 5 that show this picture. And it's an extremely important picture for understanding the relationship between functions, their first and their second derivatives. The top graph is the function. Middle one is the first derivative, bottom one is the second derivative.
Okay.
Let's first of all, I kind of want all 3 of them on there at the same time. Hold on. It's not important you see the function, but notice that the horizontal axis is x in each case. But the first vertical axis is y, the second vertical axis is y prime, and the third one is y double prime. Notice that when the original function, hold on, I do want to draw on this, so let me take a snapshot of this. When the original function is increasing from there to there, first derivative is positive. Ignore the fact that the first derivative is decreasing. The only thing we know is that if the original function is increasing, the first derivative is positive. If the original function is decreasing, the first derivative has to be negative. The original function turns back up and starts increasing, first derivative is positive again. So that's the first thing. The most important relationship is that when the function is increasing, first derivative is positive. When the function is decreasing, first derivative is negative. Now, let's look at the second derivative, which is merely the first derivative of the first derivative, right? So if I look at the first derivative, where the first derivative is decreasing, my second derivative has to be negative, and it is. Where the first derivative turns and starts increasing again, my second derivative has to be positive where it is. And the second derivative should be 0 at the extrema of the first derivative, and it is. Also, look where the inflection point is on the original function. If you drop that straight down to the second derivative, that's where 0 is. In other words, if I keep extending that dotted line all the way down there like that. So by having all 3 of them in a row here, under one another, you really can figure out this problem with increasing, decreasing, positive, negative, concavity, relative minimums, relative maximums. This is really good to understand this completely so that when they give you the first derivative, you can work backwards.
Mm-hmm.
So let me close this out. Oops. I hope I didn't close your thing out. So, again, what is the original function doing between those 2 points?
Increasing.
All right, I'm just going to take a point and arbitrarily increase it to there. That would make sense. Okay.
Okay.
What is the function doing between this point and this point?
Decreasing.
Okay, that means there's probably a little top there, and it's going to decrease all the way to there. What's the function doing to the right of 4?
It's increasing again.
Okay, that means there's probably going to be a little bottom there, and it's going to go back up like that. Now, these slopes go from steep to flatter. Hold on a second. The first derivative slopes are increasing. So I probably need to draw this with a little more curvature like that. You see where that matches the first derivative a little better?
Mm-hmm.
Because, in other words, the slope, hold on a second, I think I might have it wrong. The slope at -4 is 0, and then it's small, and then it gets big, and then it gets small again. So, I think I have this wrong. Let's try something like, let's see, the slopes. It's very easy to get confused here.
Mm-hmm.
So my slope is small at first, then it gets bigger, and about there it reaches the maximum steepness, and then it stays relatively the same for a while, and then it goes down again, like that. In other words, the slope right there is 1. The slope right there is 2. The slope right there is 1 again.
So shouldn't on the
That's a measure of steepness of slope. Well,
on the original, shouldn't it still
that's
be
the
increasing?
steepest slope right there at -3.
Right.
That's where my slope should be the steepest. Okay? But then, after -3, the slope starts getting less. So this picture, redraw it again. I believe it looks something like that. And
Okay.
I want to connect it with the other one. Let me do it this way. Whoops. Like that. Okay?
Okay.
I believe that fits everything we're looking at here. Let me just check here. We should have a 0 points right there, because I see a flat tangent line. Do we? Yes, right there. We also have a 0 point right there, so I have to have a horizontal tangent line there. So far, that picture fits pretty good. Concavity changes there, so I'm expecting we're going to find an inflection point around -2. Now, you might say, well, how come I drew it this way, and I could just as easily have drawn it that way? That blue line also fits this first derivative curve.
Right.
Exactly. In other words, I also have a 0 point right there. That comes right there. That's a flat tangent line, also up here. And so I may have neglected to check one or two things here. I know the slope when x is 0 is -2. Well, I've got a slope of what could be -2 there at x equals 0. So the question becomes actually the answer is that all of these are correct.
Isn't that because when you take the derivative, the constant in the function just,
yes,
it goes away?
Exactly. In other words, the only difference between these three functions, the red, the blue, and the green, is a constant vertical shift.
Right.
And when I take the derivative, that constant vertical shift disappears. So when I have a derivative function and I'm trying to figure out the original function, I actually can get a shape, a perfect shape of the original function. I just don't know where it's at on the y-axis without further information. And that's why they say do a possible f of x, not the f of x, because we don't know the f of x. They gave us an initial condition, we'd be able to place it vertically on that axis. But at this point, all we can do is draw a shape. Basically doing what I did there. Now, there's a couple other things I might do. We only have a minute or two here, so let me just talk about these. To get this a little more accurate, because I'm not positive I've got the concavity right. So let's draw a first derivative curve of the first derivative, and that'll tell us about concavity. So if below the first derivative I try to draw the second derivative curve, well, let's see. First derivative is increasing, therefore the second derivative has to be positive between -4 and 1. And then second derivative has to be 0 at 3. Yeah. I'm getting lost in my train of thought here. Not sure it's necessary to draw the second derivative curve. Actually, the way I figured out this concavity should be right based on that picture. In other words, from 4 to 3, my slopes are increasing, right?
Right.
That is that part right there, concave up. If my slopes are increasing, I'm concave up. This is a tiny slope right there at 4. or minus 4, and then it gets to be a steeper slope at minus 3 and a really steep slope right here. Right there where I'm pointing, and I keep remembering you can't see where I point with my cursor. Sorry, if I pointed with my mouse, I was pointing right there. So I'm pretty sure of that concavity.
Mm-hmm.
And then from minus 3 to there, the slopes are decreasing, which is concave down. Notice how in that second part, my slopes are decreasing. They're steep and then getting flatter, smaller.
Mm-hmm.
So having this as the picture makes a lot of sense. And we also know if we did take the second derivative, the 0 mark comes at minus 3. So I should have an inflection point at minus 3. You see why? In other words, I know my inflection point comes, that's why I was thinking the second derivative, because that tells me where my inflection point for concavity purposes is.
Mm-hmm.
And it's where the tangent line is horizontal of the first derivative. That means the second derivative is going to be 0 at minus 3. That means minus 3 is an inflection point. And let me redraw this a little more accurately. I know that my inflection point occurs right there. So I've got to be concave up and then concave down. Like that. Now that fits it perfectly, I believe.
Okay.
And then I have a flat horizontal tangent line at minus 1, which corresponds to that. And then I have another horizontal tangent line at 4, which corresponds to this. The only thing I didn't do is put concavity on the part between 0 and 4. And we can do that. In fact, between minus 1 and 4, since the first derivative is down there, it's going to do the opposite of that.
Okay.
In other words, it's going to be concave up and then down. So,
and the point of inflection would be around 1, right?
Yes, exactly. The point of inflection would be right there, and then it would go like that and like that. So now, if I erase just a little bit of this, we're honing in on the exact shape of that curve by just really studying, well, not just the first derivative, but the second also. In other words, the second derivative is what told me where my inflection points were. I didn't really need it. I know the inflection points are going to come right there and right there. So I don't actually have to figure out what the second derivative looks like. I just have to know that I'm going to have 0 points on the second derivative at minus 3 and 1. And
Right.
that's inflection points at minus 3 and 1. And now the curve looks very normal. I know exactly how to draw it. And the only thing I don't know how to do is where to place it on the y-axis. But I am virtually positive that the shape is very much like that.
Right.
All right. Chris, going to let you go.
All right.
Do we have another one scheduled? I was just...
I think we have one next Wednesday.
Let me just double check. Yep, at 4 o'clock.
All right.
I'll talk to you then.
All right.
Bye-bye.
Thank you very much. Sorry I was a little late.
Oh, no problem at all. Bye-bye.